Welcome everybody to this webinar about engineering. Thank you, Emma, for the introduction. My name is Oliver Hadeler. I'm a bi-fellow in engineering at Mary Edwards College in the University of Cambridge. And I will talk a bit about my journey into engineering. I will talk a bit about what you can do as an engineer, what you might expect when you're studying engineering or when you work as an engineer. And there will be a short introduction also about a little bit of some maths, just to give you an idea how engineering might be taught at university level. So let me start with my journey from physics to engineering. I actually studied physics at the University of Frankfurt. And for my diploma thesis, so my master thesis, my final year project, essentially, I was working at an experiment at CERN, the European Center for Particle Physics. And in a sort of poetic way, we were trying to understand what keeps the world together at its innermost core, which is this sort of eternal quest of humankind. And so from a physics point of view, that means verifying the standard model of particle physics, which has the Higgs particle at its center. You might have heard about it, and you might have heard that the person who predicted the Higgs particle, Professor Higgs, he died recently. And what we are looking at here is essentially this phase diagram on the right-hand side of the screen, which is similar to a phase diagram of water. On the vertical axis we have temperature, and on the horizontal axis there's a chemical potential, which is a bit like pressure or something like that. And we have the atomic nuclei on the bottom, in the middle, and then when we go up, we get into what's called a quark-gluon plasma, which is actually breaking up all these nuclei into their fundamental particles. You get this sort of particle zoo. And the question really was, how does this all work together? How do we go from the quarks to the protons and neutrons in the nucleus? And this is partially also like how to understand the early universe. And when I was working there at CERN, we worked at this SPS, the super proton synchrotron here on the left-hand side. And the particles would kind of come from this, as they sort of smash together, they would form this quark-gluon plasma. And then as they cool down, they would become normal nuclei. So they would kind of come down to this bottom part here of the phase diagram. And then later on, you would get more powerful particle accelerators like the Large Hadron Collider, which sits here on the left, which gets kind of even closer to the conditions of the early universe. So this is sort of the idea behind these experiments. And you can see here a photo of one of the detectors. They're quite small by modern LHC standard, but you can still see the size of these detectors compared to the people standing there. So the person on the left was my thesis supervisor, and the woman on the right, I think she became a professor of particle physics at the University of Warsaw, and then also worked at the LHC. So what we got there in these experiments is these particle tracks. You might have seen that in physics books or in sort of popular science books on particle physics. And from these tracks, you can determine the energy and the momentum of the particles. You can calculate their mass, you can identify them. And so that's all the sort of physics going on there. I myself was actually working on sort of detector calibration. So we were actually using laser beams to generate some particle tracks, or to generate tracks which look like particles to the detectors. And because we knew where these laser beams were, and we know that the laser beams are straight, we could then check if the detectors would actually detect these beams at the right position. And if not, then one could use correction algorithms to calibrate these detectors. It's essentially kind of, if you look at image distortion, how can you reverse an image distortion and get everything straight? So that was my contribution to this experiment, actually, of working with lasers. And I then went on to do a PhD in optoelectronics at the University of Southampton, using my sort of optics background, using this sort of laser background from the particle physics experiments. And there I was looking at fiber optic sensors for civil engineering structures. So what we had here is, on the left-hand side, you can see some fiber optics, and inside these tubes, there are sensors. They measure strain and temperature. And this whole thing here on the left is a cast for a concrete beam, which you can then see on the right-hand side in a testing rig, which applies a pressure to the beam and eventually cracks it. So the idea here is to measure the strain inside a concrete beam, and then figure out how it behaves. How much does it deform? At what level of load does it break? And this, of course, has real applications. You can put these fiber optic sensors onto bridges, for example. And this allows civil engineers to monitor bridges continuously. So you can find out if there are small cracks forming, if these cracks become bigger, if the bridge becomes unstable. So you can actually do preventive maintenance before it breaks, or by monitoring it, you know whether it is still safe. So you know there are cracks developing, you know that you will need to close the bridge at some point. But if you are able to continuously monitor it, you can work in a safe environment. And maybe you can close the bridge down during the holiday season when there's less traffic and there's less traffic disruption. And this is in the end, it's a financial decision as well. So when do you close a bridge, for example? Then, because I was working with fiber optics and these sort of fiber optic sensors, I was also exposed to telecoms, fiber optic telecommunication, fiber optic broadband, essentially. A lot of my colleagues at that time would move into telecoms because there was a real boom in the telecoms industry. But as you might know, that bubble burst in the early 2000s. The growth curves didn't sustain, and companies closed down, made people redundant, and so on. And I actually moved into liquid crystal research, first at the University of Southampton and then at the University of Cambridge. And I was looking at liquid crystals for telecommunication applications. So you might know liquid crystals from liquid crystal displays, laptop displays, but you can also use them in telecoms, in telecommunication. And what you see here on the screen are microscope images of liquid crystals under a polarizing microscope. So the light actually is polarized as it goes through the liquid crystal. It changes its polarization, and when we then sort of see it through the microscope, it's either dark or it appears in different colors. So this is all optics. And if you look carefully, you see that on the image on the left-hand side, you get these sort of dark crosses. That's where no light is going through the sample because of these sort of crossed polarizers you might have seen in physics, in your physics classes. The photo in the middle looks very different. It's a bit like a fan structure. You can kind of make out maybe some kind of big triangles in a way, either colored triangles or dark triangles. And they're also visible in the image on the left, on the right. But there, these fans also have some sort of circular lines going through them. So the structure looks slightly different from the one in the middle. And these different structures, these different optical images are caused by how the liquid crystals arrange. I will show you that in a few minutes. The interesting thing really here with liquid crystals for me was that I was working together with chemists, physicists, and engineers. And you can see a chemical structure here of a liquid crystal. This is cyanobiphenyl. So you have a cyano group here on the right-hand side, the carbon and the nitrogen, and then 2 phenyl rings in the middle, and on the left-hand side, a carbon chain, 5 carbon atoms and 11 hydrogen atoms. This is a very, very basic liquid crystal. This is how the chemical structure looks like. And the chemists can synthesize lots and lots of different liquid crystals. And here is a very small selection. And you can see maybe they all follow sort of the same principle. You have these rings in the middle, and they're quite rigid. And you get sort of end groups here, R1 and R2. And those can either be simple carbon chains or slightly more complicated carbon chains, but they're typically kind of, they can wiggle around. They're not as solid as the center. And then maybe you put some side groups here as well, these fluoride atoms. Yeah, and you can imagine if you change the chemical structure, then the physical properties change. And if we look at the physical properties, we can then move on to engineering applications. So we were always working in a circle in a way. The engineers might come and say, well, we want to have liquid crystals with certain properties. The physicists would have characterized these liquid crystals, checking what the physical properties are, and maybe find some relationship between physical properties and the chemical structure, to then go back to the chemists to say, well, could you maybe make that chain at the side a little bit longer or shorter? Could you add another ring in the middle? That might help with certain physical properties, and that would be beneficial to the engineers. And in terms of physical parameters here, the two important ones were the temperature ranges over which these liquid crystals work properly, and also the switching times. How quickly can you switch a liquid crystal with an electric field? And that's what happens in your liquid crystal display. Each pixel is addressed by electric signals to switch these individual pixels on and off, or even switch them on partially, so you can actually change the intensity continuously of the light coming through. And if you look at some liquid crystal televisions, they would, for example, give you the switching time, and they would also give you the contrast ratio. How dark can you make the black, and how bright can you make the white, and how quickly can you switch that display, which is important if you watch fast moving images like sports events or action movies. If the liquid crystal is too slow to switch, you get sort of ghosting effects. The ball doesn't fly through the image properly, for example. And so that's where the engineers want a proper display, a proper television, and then they work together with the physicists and chemists to actually get the right liquid crystals for the application. So here's a diagram of liquid crystals. So what are they actually? On the right-hand side, you see what's called the isotropic phase. You see these elongated molecules, and they just randomly orientate. So there's no order. And that's of the liquid phase. Yeah, it's like water molecules just floating around without any order. But then when you reduce the temperature, these molecules start to form an ordered phase. So they all line up in the same direction. And that's what you saw on the left image, the left microscope image. You can imagine that there's sort of two different refractive indices here. One is along the axis of the molecule, and the other one is perpendicular. So it's a birefringent material which changes the polarization of the light. If you then reduce the temperature even further, these molecules will start to align also in layers. So for example, these rigid rings, they will want to form a layer. So you can imagine that you have the sort of solid rings here in the middle of these molecules, and then the wiggly ends sticking out top and bottom. Yeah, so you get this sort of layered structure, which was the middle image, where you get this sort of fan-like image under the polarizing microscope. And then you can decrease the temperature even further, and these molecules start to tilt, which then introduces these sort of semicircular dark lines in the fans. And if you then decrease the temperature even further, you come to the crystalline phase, where everything is ordered, nothing moves, and we actually have a crystal. So the liquid crystal is sort of sitting between the crystalline phase and the liquid phase. And you can do a lot of calculations here about the optics and how fast they switch. You can do a lot of experiments, and so it's really sort of physics, engineering, chemistry all working together. Now, they're not only display applications for liquid crystals, but you can also use them in optical telecommunication. So here's an example where we had sort of a plastic substrate, FR4, and then there's a copper track here for an electric signal, and another electric contact on the top. So there's an electric field going from the top to the bottom here. And in between, there is an optical waveguide, so light can travel here from left to right. And as it goes through this liquid crystal well here, the optical properties of that light can be manipulated. So this is almost like a pixel in a display, but here the pixel actually is in an optical waveguide. So what we can do here is we can build miniature optical devices where we don't have electric currents flowing through a circuit board, but we actually have light going through a circuit board, and we can manipulate the properties of the light, the intensity or the polarization or the speed with which it travels. And there are potentially a lot of different applications for this. But when I was doing this, this was during the time of the, just before this of telecoms bubble burst. A lot of people were interested in this. And then suddenly interest in this sort of area dropped away. So there's not that much research going on in this area anymore. And even like with the liquid crystal displays, if you go to the shops now, a lot of the televisions are OLEDs, organic LEDs. And this is actually the new technology which has sort of superseded the liquid crystals. There are still things where liquid crystals may be useful in some microwave electronics. There's a lot of research going on in these areas. But liquid crystals for displays, that is probably in the past. So then, because the kind of liquid crystal research maybe is dying out, I left research and started to work in the University of Cambridge as a person to support researchers across the whole university. And this was all in the field of sensing. So this comes back to my fiber optic sensors in the civil engineering structures. And here I was working with biologists, chemists, engineers, physicists, medics, and even arts and humanities. So really across the whole university. And we are bringing together the researchers, the PhD students, the professors to cross-fertilize our research. So you can see on the bottom, you see lots of people from lots of different departments, and they all came together for sort of a hackathon in combining electronics and biology or biochemistry. So you see in the top left photo, it's some sort of experiment in biochemistry, but there's a lot of wires here as well. So it involves electronics. So even as a biologist, you might need to know some electronics. And that is much more accessible nowadays with sort of open source electronic boards like Arduino boards or Raspberry Pis. And so now we really sort of engineers can work together with people who are not working in the physical sciences and actually build new devices. And that's really exciting to really sort of work with this broad pool of people. And I'm now actually a lecturer at UCL in electronic and electrical engineering. So I have left Cambridge more or less. I'm still a By Fellow in Murray Edwards College. So I still contribute to the teaching and learning in the college itself. But my main job actually is in London. And there I teach mathematics, the Internet of Things, and I'm responsible for student projects, and I also run quite a number of undergraduate projects. And you see, this is kind of typical of electronic and electrical engineering today. We have researchers here on the left working in optics, and on the right is some undergraduate students doing some simulations, some circuit testing in the teaching lab. So what I want to say with my story really is that your future is not set in stone. Yeah, so whatever you study doesn't mean that you have to follow a certain path. You all determine your own path, and it really is one step after the other, and one decision leads to another. But it's not that if you study physics, you will always be a physicist. If you're an engineer, you will always be an engineer. Or if you study civil engineering, you always will be a civil engineer. Yeah, there's a lot of different pathways. And the technology and also society, they move on, and you need to move with it. And so when I say, for example, the liquid crystal research has changed, I needed to move on. I needed to do something else. And the interesting thing really is, as an engineer, you can shape the technology. You can shape the society. And the engineering departments in UCL, they have this strapline of changing the world. Yeah, as engineers, you can actually change the world. I will show you in a moment how this might work. So you're probably at this point now where you need to decide what to study. And I was at that point as well many years ago. And one of your questions might be sort of you're thinking about mathematics, physics, engineering, and what's the difference? What do you want to study, and how is it? How do these different subjects work? I will try and explain a little bit about this. So maybe when you think about mathematics, at school, you're doing a bit of geometry, calculus, statistics, maybe some other topics as well. And they might appear as tools. Yeah, you might use the mathematics in other subjects. So when I was looking, or when I was deciding what to study, I looked at mathematics as well. And at that time, mathematics was used in insurance and in finance. So you could use statistics to calculate insurance premiums, or you could use calculus to model how economics works, how economies work. And I didn't find that terribly exciting. Nowadays, mathematics is used in artificial intelligence, in image processing. So it's actually maybe much more exciting, at least for me, it would be more exciting to study mathematics now, because I can see much more interesting applications for myself. But then mathematics is also about the concepts, the proofs, the unsolved problems of the mathematicians. Yeah, so have a look at maybe the mathematics webinar, have a look at other information around mathematics. And in this area, mathematicians look for things which are always true, which are true everywhere. Yeah, 1 + 1 is 2, whether that's here on Earth or at a galaxy far away. And you have theorems like Pythagoras. They are still true. They were discovered by the ancient Greeks, but 2000 years later, they are still true. Then there are prime numbers. They are used in encryption, and they are one of the still unsolved problems. And we can easily multiply 2 large prime numbers together to get a new number and use that in encryption. But if I give you a really large number, 100 digits or so, it's very difficult for you to break it up into 2 prime numbers. And so the encryption works one way, but not the other. And so that makes the internet safe. But if there are some mathematicians coming and actually finding out how to generate and how to find prime numbers quickly, then maybe our encryption falls apart. And these are real sort of mathematical problems which have engineering applications. Now, if you work as an engineer in sort of computer science or computer engineering, encryption is something which you will come across very often. And then in physics, I already sort of hinted at that. It's to describe and understand the physical world. And we have the experimental evidence and the observation on one side, and we have the theory, which is based on mathematics, on the other side, and they feed off each other. So you have in particle physics, you have lots of evidence from your experiments, and how does that compare to a theory? Or somebody develops a new theory in particle physics, can that be experimentally verified? And that's true for other things as well. You have maybe Maxwell's equations and the prediction of electromagnetic waves, which were then discovered by Heinrich Hertz. And then you have this, you always go backwards and forwards between the theory and the experimental evidence. And of course, the question then is, can these findings from physics actually be used in the real world? So if you just think maybe back to Maxwell and Hertz about the electromagnetic waves, that might be interesting to look at for a physicist, but actually that's radio, right? And that's our 5G communication. So this sort of discovery of electromagnetic waves, both in theory and in experiment, actually has a real application, which then is driven by engineers. And you can phrase this question here also in a different way. Is it a good way to spend taxpayers' money to run these sort of big physics experiments, for example? So here's another example of particle physics. So on the left-hand side, this is an experiment at a heavy ion accelerator in Darmstadt near Frankfurt. So again, rather large experiment, expensive experiment. And then on the right-hand side is a diagram. It's in German. The horizontal line is the depth, how far particles penetrate human tissue, and on the vertical axis is the amount of radiation you, the dosage of radiation you put into the body. And you can see that here the Röntgenstrahlung, the X-rays, they penetrate 5-6 centimeters or so, but there's a long tail, right? They sort of really go through the whole body. It's you can't actually focus them on anything. But if you have the ions from this sort of heavy ion accelerator, then they really get absorbed in one particular region here, and you can change where they get absorbed. So I can actually use these ion beams to treat a tumor at a certain depth inside the body. And this is actually used. It's not just theory or some experiment in a big physics experiment, but it's actually used in this sort of heavy ion therapy center in Heidelberg. So there's on the left-hand side in the photo here, the number 3, that's the accelerator. And then there are different treatment rooms here. And you see sort of a diagram here in the end. So it's all very clean. It's a very different environment from the particle physics experiment itself. And so here it's where you use physics to treat patients. And there's a lot of engineering going on in between. Yeah? So just to take the physics and convert that into into a real treatment, medical treatment, you need a lot of engineers, medical engineers, biomedical engineers, to translate the physics into the medicine. And I was talking to one of our medics here at Murray Edwards College, and he said a lot of the medical advances are actually driven by engineers. So without engineers, modern medicine wouldn't progress as fast as it does. And of course, there are the pharmacists and so on developing new drugs. That as well, but it's drug development and it's engineering which drives the medical field forward. So what is engineering? I mean, that's why you're here, and I've been talking about physics and all sorts of other things for quite some time now, but I always hope to bring in the engineering. It's always there, even when I talk about physics. These are some images Microsoft proposed to me when I said, well, I want to talk about engineering. The top right image, of course, again, is physics. Equation of gravity on the top here, and Einstein's relativity equations. But then on the top left, sort of information technology, lots of ones and zeros, and on the bottom left, the electronics, a lot of black boxes with a lot of pins, a lot of legs on it, and you can't see anything. If you open your smartphone, it's full of black boxes. But there's a lot of engineering going inside these black boxes. And then on the right-hand side, civil engineering, structural engineering, things you can actually see, right? Like a crane or a bridge. You can look at them, you can marvel at them, and they're much easier to see and to understand than the electronics here on the left. But nevertheless, this is all engineering. Yeah? It all comes together. So here's a list of engineering disciplines. So you have civil engineering, structural engineering, mechanical, electronic, electrical, aerospace, chemical engineering, biomedical engineering. So there's a whole range of different engineering disciplines, something you don't get in physics. Right? Physics is experimental physics and theoretical physics, maybe applied physics, the kind of three themes. And but you can't study experimental physics as a course normally. It's the course will always have everything. The only difference you get in physics maybe is if you have physics and you have astronomy. That astronomy is different. But engineering really splits up into all of these different disciplines here, and they're often in separate departments. And I think that's not necessarily a good thing. So if you go to Cambridge, for example, Cambridge has one engineering department, and all of these things here on the left are taught within that department, apart from chemical engineering. Chemical engineering is separate, it's chemical engineering and biotechnology. But everything else you can do in one engineering department. At UCL, the departments are separate. They're all in the same building, in the same faculty building, but there are different departments on different floors. But the students work together. There is an integrated engineering program where students from different engineering disciplines actually work together for some time to learn from each other. And you will find that in other universities as well. If you go to other universities and look at their engineering websites, more and more of these universities will actually have cross-disciplinary elements in their courses. So if you become a mechanical engineer, you hopefully learn something about electronics. Maybe you learn a bit about civil engineering or structural engineering. Yeah, so there's a lot of overlap nowadays in engineering. But there's some common themes there, right? And engineers try to find solutions and making our world better. And I said earlier, change the world. And it's all based on scientific rigor. So you can't just go and do something. You actually have to base this on physics and on maths. Typically, as an engineer, you work in teams, and more you're working across disciplines. So you're not siloed into one particular theme of engineering necessarily. So here's an example of what engineering is nowadays. This is a smart glove from MIT, from Cambridge in Massachusetts in the US. And this glove here in the big picture, it has sensors on it, and it has a little bit of sort of feedback in it as well. And you can use that, for example, to control a robotic arm here on the left. So if you make a grabbing movement with your hand, the robot will mimic that and sort of pick something up. Or you can maybe here the bottom is, I think the idea is to help students learning how to play piano. So on the left-hand side, the teacher might have a glove, and the glove senses the pressure on the keyboard, and it transfers that pressure onto the glove of the student. So this is all about, there's a lot of sort of electronics in there and robotics, which robotics need the mechanical engineering again. So it's again sort of cross-disciplinary. Or the piano playing, it goes into the arts. Yeah, so it's a lot of different things one can do as an engineer. Or another example here, vertical farming. This is a photo from Nottingham Trent University. They use sensors and the Internet of Things, plant science to grow plants in a greenhouse. And it's also about the economics of that, right? How much energy do you need to heat that greenhouse, to provide light to the plants? How much water do you need? And can you make this greenhouse energy efficient, cost efficient? And for that, you need engineers who understand how the sensors work, how the data is transferred or transmitted on the internet to a cloud server. And so there's a lot of different things going on here where you need engineers to actually understand how this works. But then the engineers have to work with the plant scientists. You can't just have engineers who don't understand the plant physiology or the plant biology. So you really need to work across disciplines. And now there are sort of, initiatives about looking into the future, engineering towards 2030, which is a few years in the future, and will probably affect you. If you study engineering now, you will be ready for your first career steps in 2030. And a big theme are the United Nations Sustainable Development Goals. There are 17 of them here. And essentially, every single one of these goals needs engineers. There are some obvious ones. If you, let's say, on the top right, number 6, clean water and sanitation. You need civil engineers to work with water supplies and with sewage treatment. Yeah, this is done by engineers, by civil engineers. You have what else? On the number 14, for example, life below water. How do we keep the water clean? How do we, what else? Number 3, good health and well-being. You know, the biomedical engineers. So that's, reduced inequalities, number 10. How do you make engineering, or how do you make devices and products accessible to everybody, no matter what your background is, no matter if you have a disability or not? How can engineering help people? And of course, climate action on the bottom left, right? Everything to do with renewable energy, with carbon reduction. You need engineers. They use the principles the physicists have found, but it's the engineers who really sort of apply that knowledge and find solutions. So this is really the excitement here, where you need engineers. And if you look at some universities, you find that engineering departments celebrate something between 100 and 150 years of existence. So they started in the late or mid 19th century. And that's of the back end of the first industrial revolution, the sort of steam engine, and you needed the engineers to actually understand how the steam engine works and how to make it more efficient. It then moves into electricity generation, electric power, and how to harness that, how to work with the first radios, how to work with the first radar systems, and so on. And now we are looking into the future, 2030 and beyond. How do we, as engineers, solve the problems we are facing as humans? That's really where engineering comes in. Now, this is all very exciting, maybe, but it requires a lot of rigorous work. And I just want to show you this as a very brief example, really. So bending beams, coming back to a bit to my concrete beams from my PhD thesis. So you have that image again here on the right-hand side, but on the left there's this is an aircraft wing, or it could also be the blade for a wind turbine, for example. How do these structures bend? And we can measure this, we can calculate that. And that really, it needs a lot of work. So here's a sort of typical diagram. On the left-hand side, there's a beam which is supported on the left, and you apply a force downwards on the right, and of course the beam bends. And if you take a rectangular beam which has a width of b and a height of d, then you can get these sort of equations here. So on the left-hand side, there is the beam is actually going here from z equals minus d over 2 to z equals d plus over 2. And here in the middle, where z is 0, that's where when you bend the beam, that's where it neither stretches nor contracts. Yeah, so on the bottom, the beam is contracting. On the top, the beam is expanding. And in the middle, it's neutral, nothing happens. And then you look at things like what's the angle here? What's the bend radius? You need to talk about small sort of changes in L and D and so on. And you get, after some calculations, you get to these sort of equations here, which is m is the bending moment. So the idea here is that on the top of the beam, I have a force which points to the right. It stretches the beam. On the bottom, I have a force which goes to the left, and it compresses the beam. And if I take a point in the middle here on this neutral part, then I get a couple. Now I get a distance the center to the top times a force to the right, or distance to the bottom and a force to the left. And you might have seen that in physics or in maths. It's this sort of couple of two forces going in opposite directions. And you can do this for small elements in this beam, and then you need to sum them all up. You need to integrate. You need to integrate from minus d over 2 to plus d over 2. There's some constants in here which you can put in front of the integral, and then you can do this in your own time, as we would say in the lectures. Integrate z square from minus d over 2 to plus d over 2. To come to this equation here, a lecturer would take half an hour. And there would be steps in there where they would just say, well, you just have to believe me. Go home and try it out for yourself. And so it's not like at school where every single step will be explained. There will be a lot of big steps, and there will be a lot of homework for you to do. And then once you've done all of that, you can look at the maximum deflection at the end of the beam. You can also look at the strain inside the beam, which is actually maximum at the support side on the left, in this diagram. So the strain really is biggest here at this point on the left where it's supported, and the maximum deflection is this bit over here. And after some calculation, you end up at these sort of equations here. And then typically, you probably want to do some experimental verification. So here's an experiment. This is sort of a wooden beam. It's a wooden fork. There's a strain gauge over here at the support. And then there's some weight here and a ruler in the back, so you can measure the deflection. And you can measure the strain here with a strain gauge using some electronics and a Raspberry Pi to record the data. So this is kind of a typical what you probably would do as an engineer to verify your equations, do experiments, try and find out what are the measurement errors and so on. Now, I mentioned before that engineering tries to solve problems in the world, and I just want to show you an extract of 1 or 2 videos here showing you how engineering and society work together. So the left-hand video is on hacking a car.
Around the world, it can be remotely hacked over the internet through a cellular connection to its entertainment system that would allow someone to take over its steering, its transmission, and even its brakes.
Yes, so here some ethical hackers have hacked into the entertainment system of a car, and they will be able to take over this car. They can switch off the brakes, they can control the steering. And this is where, as an engineer working in electronics, in Internet of Things, as an automotive engineer, you have to keep in mind what can go wrong with your technology.
No shoulder to escape onto. Okay, do it. Do it. Kill the engine. So we're killing the engine right now.
So they've just switched off his engine on the motorway. And the solution is to switch off and on the car, a bit like a computer when it crashes. But you have a computer on wheels, and that has its problems. And here at the end, they switch off the brakes.
Their stunt on the highway. Chris and Charlie still wanted to show me a couple of other tricks. Below a certain speed, they can control the Jeep steering as long as it's in reverse. Pop its locks, mess with the speedometer, and of course, disable the brakes. Okay, hold on tight. Hold on. He's not getting out of that. That's tight.
Yeah, so they just well, he can't brake, and so that's a problem, right? If we all think about autonomous cars or self-driving cars, if somebody can hack them, we don't really know what's happening. And then here on the right-hand side, it's about, so this is a parody, but this is about a smart fork here, which will monitor this gentleman here. Let's see if this works. So he likes to eat his fried bacon, his baked beans, and so on. But his daughter gave him a smart fork, which actually monitors the nutrition. So now he's using that fork, and his daughter can monitor what he's eating. So she's quite happy that he's using this new device. But he also has a smart walking stick. He's monitored when he goes to bed. And there he is now, he is actually, he stops using his fork. And he just puts the fork on the side here, but his daughter can monitor the usage of the fork. So he will ping him and say, look, what are you doing? Why are you not using the fork? And but luckily, this man actually finds a solution to it. There it is. He puts the fork in the salad while he's eating his fried food, and every now and again he will move the fork in the salad just to pretend he's eating healthily. So there's a lot of misuse of engineering solutions possible, and this is something one has to think about as engineer, right? Engineering is not happening in a vacuum. It happens together with in society, and for all of these reasons, we really need more engineers, right? We need to solve our problems. We need to solve them in an ethical way. We need to solve them in a safe way. And you might have seen lots of videos and news and so on with sort of cool engineering solutions. But as I also tried to tell you very briefly, it needs a lot of rigor. It needs a lot of math and equations. Some of them you have to learn by heart. Others you have to be able to derive from first principles. So it's a lot of hard work, but it's also a lot of fun. And with that, I will stop, and I'm happy to take questions.
Great. Thank you so much, Oliver. Thank you for that. That was really interesting, very informative. Yeah, I love that last slide. We need more engineers. Fantastic. Yeah, I've been having a look at, we've had loads of fantastic questions, and we are a little short of time. But perhaps I'll just pick out a couple if you're okay to answer a few. And I must say, if anyone else doesn't get their question answered and really wants their question answered, then do email the outreach inbox. It was the inbox that sent the webinar link to you, and we will do our best to answer any further questions. But here we go. Let me have a little look here. This is a good question, I thought. How much practical lab work is there on an engineering course, and what does it entail?
There's quite a lot of lab work. I would say typically you have lectures in the morning, and then you will have probably 3 hours of lab work per week, depending, of course, on the course and the university and so on. But usually it's like in Cambridge and UCL, it's probably about sort of 3 hours of lab work, and that is either short labs which support the lectures, or it could be longer projects. So there could be, like in Cambridge, for example, in the second year, students do an integrated design project. This is using all the engineering disciplines together to build a robot. And that runs over 4 weeks. So it's really, and there you have to, as a student team, you have to manage your own time, and you go into the lab almost whenever you like and spend lots and lots of hours trying to build your robot. So it can really be from like a 1-hour, very structured session to labs which last several weeks.
Brilliant. Thank you so much. Okay. Here we go. Do you have any book recommendations for someone who wants to study engineering, and where you might find useful resources?
I personally don't have any book recommendations. I see if you go to, certainly if you go to the engineering application site in Cambridge, there is a book list, and we always get students who said they read the books. And I would say whatever really interests you, if depending on which area of engineering maybe you want to go, read about those topics. Yeah, have a look at the, let's say, at the University of Cambridge recommended reading list, or also other universities, and see what they suggest. But I personally don't have any one particular book. I mean, sometimes it's also maybe just good to just go to a library and have a look what you find, or go to a secondhand bookshop. I just recently picked up a book on prime numbers in a charity shop, which is interesting.
Brilliant. Thank you. And I think we will have one more question. There are so many questions, and they're great questions in the chat. So please do send them to Outreach inbox, and we will do our best to answer. But there's a question here around sort of specializing. So do you think an aerospace engineering degree would be worth it, or would it be more useful to study mechanical engineering and then specialize in the workplace?
That's an interesting question. I would say it really depends on the course, and also on what you want to do later on. And there are some universities where there's a lot of cross-disciplinary work, especially, for example, in Cambridge. In other universities, you have to specialize in one or the other. But it might be really useful to look at the courses and see what is in them in more detail, whether they cover the topics you're interested in. And you can always go from one discipline to the other, as I said, and that might be sort of specializing in the workplace. If you do, let's say you're a mechanical engineer and you want to go into aerospace, try and get a job in, I don't know, Airbus or Rolls-Royce or whoever, and use your mechanical skills there, and then become an aerospace engineer. And you can probably do the other way around as well. You can use your aerospace knowledge and use that in mechanical engineering.
Fantastic. Thank you, Oliver. That's brilliant. I think we'll leave it there for questions. There's been a lot of questions around subject choices and the types of A-levels, and whether or not you should do 4 or 3 A-levels to come to Cambridge for engineering. Just to say to everyone, all of that information is on our website, Murray Edwards College, but also on the main university page. So do give that a good read through and a good look. But we are always also more than happy to answer questions about subject choices and what might be best. So do pop an email to our inbox, and we will absolutely get back to you on that. So I think we'll leave it there today. There's been more questions around where this will be available. It will be on the Murray Edwards College YouTube channel, but I will also send a link to that to everyone who signed up for the webinar today. And on behalf of the Access team, Oliver, thank you so much. That was fantastic. And good luck to everyone on their journeys through sort of sixth form, college, and then on to university if you decide to go to university. University, and hopefully some of you will make up our future fantastic engineers. So brilliant. Thank you so much, Oliver, and thanks everyone else. Take care.
Bye-bye.